All right, welcome to calculus. We're going to start with the prerequisite chapter. There are 4 sections. We're starting with section 1 here on graphs and models. You may or may not know it, but the 2 mathematicians that are given credit for the creation of calculus, one was German, one was English, Wilhelm Leibniz and Isaac Newton of gravity fame. They were contemporaries. They're given most of the responsibility, most of the credit I should say, because they took on that responsibility. But before there was a Leibniz and before there was a Newton, there was Descartes. And Descartes lived from 1596 to 1650. It's a shame that he lived such a short life because it was due to his true genius that it paved the way for the development of what we know as coordinate geometry. And without coordinate geometry, and of course you're used to coordinate geometry with the coordinate axes and quadrants and the origin and ordered pairs, equations and 2 variables, slope, midpoint, distance formulas, and so on. Without that, the rise in calculus would have been slow going. So what we're going to do is we're going to give our credit to Descartes and also do a little bit of review, because it is a prerequisite chapter and this is primarily review. And what we're going to do is we're going to start with the idea of graphs. Now, probably the simplest of graphs would be that of a linear equation in 2 variables, as the example is here above. Now I get to try this new screen, see how this works out. Oh, this is lovely, except that my hand's all beat up. Too much yard work. So in this case it says consider the equation y equals 3x plus 5. Now this is an equation that you should recognize from your algebra days. It's the equation of a line in slope-intercept form, and we know that if we wanted to graph this line, we could use the slope, which is 3, and the y-intercept, which is 0, 5, to graph it. But what we're going to do is we're going to go to the basics. We're going to look at an ordered pair, the ordered pair 1, 8, and we're going to state that it is a solution to this equation in 2 variables because upon substitution it satisfies the equation. And as you can see here, we're going to plug the x value in for the x variable and the y value in for the y, and I would get 8 equals 3 times 1 plus 5. Hopefully you can see that clearly enough. It looks like it's coming up okay. And of course 3 times 1 is 3 plus 5 is 8. So it gives us a true statement. That's what we mean by a solution to an equation, in that it gives us a true statement to what's going on. So what we're going to do now is we're going to consider the fact, since this is just one single solution, how would we come up, since there are many solutions to this equation, how do we come up with all the others, and how do we list them? Do we write a solution set with ordered pairs? Well, there's an infinite number of solutions to this equation in 2 variables, so that idea of writing out a solution set and all the ordered pairs that are solutions is impossible. So what we're going to do is we're going to represent this infinite set, this infinite solution set, graphically. Alright, so what we're going to usually do is we create a t-chart or a table of values to represent the entire solution set with the graph of the equation, because you may have heard the old Chinese proverb that a picture is worth 10,000 words. Well, a graph is worth infinitely many points, infinitely many solutions to an equation. Now here again is Descartes' genius. We have an equation and we have an ordered pair, and that's all algebra. But in geometry, this equation is that of a line and this ordered pair is that of a point on the line. So he is using algebra and combining it with geometry, and that of course is what we know as coordinate geometry. Now, this was an equation, this was an easy one. We've had this before. But if you're given an equation that maybe you're not as familiar with, this creating a table of values and plotting points is key, because you may not know what the shape of the graph actually is. You can get probably a decent idea of the basic shape of the graph by plotting, the drawback is plotting a lot of points. Now what we can do, of course, is we can graph on the graphing calculator or even Desmos, and we can get an idea of what the graph would look like. We just have to make sure that we set our screen limits correctly. So here's a graphing calculator. Let me turn it on. And I have y equals x squared, and I'm going to graph this by pressing graph here. And you can see, well, wait a minute, that doesn't look like y equals x squared. I know y equals x squared is a parabola. Well, there again, we want to make sure that we have the proper window. Okay, so what I'm going to do here is I'm just going to plug in -10 and 10 and 1 and -10 and 10 and 1, and then I'm going to hit graph. And now you see something that you're a little bit more accustomed to seeing. So be careful if you're using the graphing calculator to check your work that you have the proper limit set for your x's and for your y's. This is a good example of that. All right, so now we take one page over to the side and we bring a new page over here. All right, I like this. No standing in front of a whiteboard for me anymore. So now I have a couple of examples here. The first example, y equals the square root of 4 minus x squared. You may or may not recognize right away. You probably should. It's maybe a little while. You did some in pre-calculus and definitely did some in algebra 2. And I've gone ahead and listed the domain and the range, although I didn't call it the range, I called it the wrangle. This is the range. I guess it helps if I proof my writing first. And I've written the domain and the range in interval notation, something again you should be somewhat familiar with. I've also created a t-chart to find some y values and then see if I can get an idea of what this graph looks like. Now if you wonder how I got the domain, because we're looking at real valued functions, I know that 4 minus x squared, and I'll put it right over here, must be greater than or equal to 0. So that would give me 2 minus x times 2 plus x greater than or equal to 0. I get key values of 2 and -2. And I would test these values by taking a number from each of the subintervals, like -10, and plug -10 in. That'd be positive. That'd be negative, so it's negative. And I take a number in here between -2 and 2, like 0, and I plug 0 in for x, and I get a positive times a positive, which is positive. And then I take a number like 10 over here in this interval, and I get 2 minus 10 is negative, 2 plus 10 is positive, negative times positive is negative. So I want where it's greater than or equal, that's when it's positive, and you can see it's going to be right in here. It is going to include the endpoints of -2 and 2, because that's what makes it 0. And you can take the square root of 0, but you can't take a real value, you can't take the square root of a negative number, that's an imaginary. So now, to get an idea of the shape, I'll plug these numbers in here. I'm trying to keep this as straight, but this is new to me, so bear with me here at first. I plug -2 in here, I get 0. I plug -1 in here, I get the square root of 3. I plug 0 in here, I get 2. I plug 1 in here, I get the square root of 3. Now remember, when you plug a negative in, it's being squared. So that's going to make that positive, and then 4 minus that positive number. And if I plug 2 in, I get 2 squared is 4. 4 minus 4 is 0. I get the 0 again. So if I was to plot these points and then see if that's enough to get an idea of the curve, I would have -2, 0 here. I would have -1, the square root of 3, which is about 1.732. I would have, I think that's pretty close, maybe a little bit further over. I would have 0, 2. I would have 1, the square root of 3. And then I would have 2, 0. And you may kind of recognize it now that this, even though my hand is not very steady, this is a semicircle. And that would be the graph there. There are infinitely many points here, and every one of those points, if you wrote the ordered pairs down and substituted them in, it would satisfy the equation. Now in this next example, this is something you're probably a little bit more familiar with. Y equals x squared minus 2x, which you should know is a quadratic function, and the graph of which is a parabola. The domain for this, excuse me, first sneeze on camera, on the video here. The domain here is the set of all real numbers, because you don't have to worry about the square root of a negative or 0 in the denominator. And so I'm going to go ahead and not complete the square, not put it in vertex form, but I'm going to go ahead and substitute some values in. -2 squared is 4 minus 2 times -2, so that's 4 minus, excuse me, that's 4 plus 4, because that's going to be a plus 4 here. That's going to be an 8. I almost said 4 minus 4. And then I plug the -1 in. That's 1 minus 2 times -1 is plus 2, so that's a 3. I plug the 0 in, I get 0. I plug the 1 in, I get 1 minus 2, which is -1. I plug 2 in, I get 4 minus 4, which is 0. I plug 3 in, I get 9 minus 6 is 3. And then if I plug 4 in, I get 16 minus 8 is 8. Now I picked those points on purpose just to have those exact points because I know a little bit about this graph, and I wanted to make sure that I could use the fact that I'm going to have some symmetry in my graph because it is a parabola. So now I'll graph these points. -2, let's see, 1, oh, by the way, before I forget, if I asked you to graph something on an assignment, I would prefer that you use graph paper, or if you don't use graph paper, if you've done what I've done, use a straight edge and measure out the tick marks in both the X and the Y axis so that it's nice and neat, and that you also notice arrows on the ends of the axes because they are lines, and also I've set the scale. I have an indicator that this one tick mark here is worth 1, and that the one tick mark on the y-axis is worth 1. I expect you to set the scale every time, even if it's obvious that you want to use 1 for both axes. Indicate that if you would, please. All right, so now I'm going to graph -2, 8, 2, 3, 4, 5, 6, 7, 8. There's the 8 right here. So -2, 8, best that I can. -1, 3. 0, 0, 1, -1, 2, 0, 3, 3, and 4, 8. And you can see the parabola probably a lot more clear. It's kind of the U shape, and you should try to draw it as neatly as possible. That's why you should do your graphs in fact, you should do all of your work in pencil so that you don't have to scratch stuff out, especially the graphs. And you want to put the little arrows on the ends to indicate that it goes on forever. That's fine as well. So there's the graph of that guy. Now I've really slowed this down. I know that you guys could probably race through these a lot more quickly than I am, but I wanted to make sure that I covered all the basics here for you. So let's scoot this off to the side. Okay. Now another thing that would help you, I mentioned symmetry in the graph that I just did with the parabola, and we're going to talk about symmetry, but another thing that would help us with our graph is to find the X and the Y intercepts. Now I actually had the X and the Y intercepts, you could see here on both of these graphs, because my X intercepts of course are the points where my graph crosses the X axis, and my Y intercepts where my graph crosses the Y axis. I have the same thing here. I have this is not only an X intercept, but it's a Y intercept because it's on both axes, and of course this is an X intercept. To find the X and the Y intercepts is usually the simplest points to find because you just plug 0 in for either X or Y. So if I wanted to find the X intercepts, that means it's going to be on the X axis, and that means that my Y value is 0. So I set my Y equal to 0, and I factor here 2x. That would leave x squared minus 4 equals 0. I can factor again, and I can see I'm going to get, oops, that's a +2. I'm going to get 3 values. I'm going to get x is equal to 0. I'm going to get x is equal to 2, and I'm going to get x is equal to -2. Now those are not my x intercepts. My x intercepts are 0, 0, 2, 0, and -2, 0. Notice that I'm writing my x intercepts as well as my y intercepts as ordered pairs because they're points on the graph, and points are described by ordered pairs. My y intercept is done just the reverse. To find my y intercept, which means that it's where it crosses the y axis, and I already know what it is because it's 0, 0 right here. But what I'm going to do is I'm going to set x equal to 0 in my original equation. I get y equals 2 times 0 cubed minus 8 times 0, which of course is 0. So my y-intercept is 0, 0, because this is going to be the y value, and of course the x value is 0. That's why I set the x equal to 0. Another really useful idea is the idea of symmetry. Now students don't normally like to test for symmetry because it takes a while. The tests are written down here nice and neat for you. The test for symmetry: a graph of an equation in x and y is symmetric with respect to the y-axis if replacing x by the opposite of x yields an equivalent equation, which means I replace the x with the opposite of x. I get right back to the original problem when I simplify. That means I have symmetry to the y-axis. And a graph that's symmetric to the y-axis, that function is and we're going to talk more about functions in the next section, but we refer to that as an even function. Now we can also possibly have symmetry with respect to the x-axis. And to find if the graph of an equation in terms of x and y is symmetric with respect to the y-axis, to the x-axis, we replace y with the opposite of y, and we get right back to the original equivalent equation. We get right back to it. So in this case, this would not be a function, because if you have symmetry with respect to the x-axis, it's not going to pass the vertical line test. And in this case, the graph of an equation in x and y is symmetric with respect to the origin. 0, 0, if you replace x by the opposite of x and y by the opposite of y, and it yields an equivalent equation. Now, real quick, symmetry. If I'm talking about symmetry with respect to the y-axis, in fact, I can come back to here, the graph I did a little bit ago, y equals x squared, because every point on the graph pairs up with another point on the graph, such that if I connect those 2 points with the line segment, that the y-axis is the perpendicular bisector. There's not a single point on this graph, other than possibly the origin, that doesn't work for, and of course that point's on the line of symmetry. Now, if I was to graph, I'm going to change this here just a second. I'm going to change this to x to the third. So let's go x raised to the third power here. I'm using an old TI-83 here. You guys are probably using the 84s or something fancy, 89s or something fancier than that. 89s, by the way, are really nice for the calculus class, for the AP test. Notice here that this graph is symmetric to the origin. And you can see that it's symmetric to the origin because every point on this line here, or on this curve, pairs up with another point on this part of the curve, such that if you connect those 2 points with a line segment, that the point of symmetry, the origin, is the midpoint of that line segment. Okay? Now, I can't really do a nice graph here on the graphing calculator that shows symmetry with respect to the x-axis, but you can think of this maybe as the unit circle. X squared plus y squared equals 1, because it's symmetric to the y-axis. It's also symmetric to the x-axis and the origin, but it's symmetric to the x-axis because of the fact that I can find any point on the circle. There pairs up another point that if I draw the line segment, that the x-axis would be the perpendicular bisector, similar to what I was talking about with symmetry to the y-axis. All right, now let's test for symmetry without having to graph. I'm going to first test to see if I have symmetry with respect to the y-axis by plugging in the opposite of x in. So for the y-axis, I have y equals the opposite of x to the third power plus the opposite of x. Y equals the opposite of x times opposite of x times opposite of x, negative times negative times negative, is the opposite of x third minus x. And if I factor out a -1, I get x to the third plus x. Now, is this the original equation? Let's go back to here. No, because of this factor of -1. So do I have symmetry with respect to the y-axis? No. Now, with respect to the x-axis, I'm going to plug the opposite of y in for y, and x in for x. And you can see here that this is not the original as well because of the factor of -1. There's nothing I can do. I can't multiply both sides by -1. I would change that to y, but then I would have the same thing over here. So this one is no. Now, the origin, different matter. Because in the origin, I'm going to plug the opposite of x in for x and the opposite of y in for y, and I get the opposite of y equals the opposite of x to the third power plus the opposite of x. So I have the opposite of y equals, I did this before, the opposite of x to the third minus x, and then I multiply both sides by -1, and son of a gun, I get right back to that original equation. So this one is a yes. And I have symmetry with respect to the origin. When you're answering the problems, make sure you answer the problems properly so that I know. Sometimes people will put an X for a no and a check mark for a yes. Well, I don't always understand your little notation code, so you have to make sure that you answer the problem properly so that I can make sure that I can see that if you know what you're doing here. All right, next page. Oh, we're having some fun now. All right, here's another example of a problem that I'm going to check for symmetry. So I'm going to check first for the x-axis, or y-axis. That's what we did the last time. Let's check for the y-axis. So I plug the opposite of x in for x and y in for y, and that yields y equals the opposite of x squared all over the opposite of x squared plus 1. Well, the right side does simplify a little bit. The opposite of x times the opposite of x is x squared, and that's x squared. Look at this, right back to the original. So yes, it's symmetric to the y-axis. Is it symmetric to the x-axis? I don't think it's going to be, but we'll go ahead, we'll plug in the opposite of y in for y. And as you can see, there's no way I can make this guy into this guy. So no here. And how about the origin? So that would be the opposite of y equals the opposite of x squared all over the opposite of x squared plus 1. So I get y is equal to, or actually the opposite of y is equal to x squared all over x squared plus 1, and I'm back in the same situation I was here when I was checking for symmetry with respect to the x-axis. So this one is no as well. So symmetry with respect, I got to try to make sure I keep this level, with respect to the y-axis. There it is. Had it there the whole time. All right, now I want to sketch the graph of an equation that you may or may not be as familiar with, because it's not a function. It turns out it's a relation, but it's not a function, so it's not your traditional graph. First, I'm going to check for intercepts here, and then if I need to, I'm going to plot some points. As you can see, I've already got the t-chart kind of set up here. So for intercepts, if I set x, for y-intercepts, if I set x equal to 0, I get y squared minus 4, which is y minus 2 times y plus 2. So I'm going to get y equals 2 and negative 2. So yeah, I have two y-intercepts. My y-intercepts are at 0, 2, and at 0, negative 2 y-intercepts. There they are. And I'm going to check for x-intercepts. So I plug y equals 0. So y equals 0 right there. And I get x equals 0 squared minus 4, which is negative 4. So I have an x-intercept at negative 4, 0. Now I'm going to check for symmetry. Well, I didn't leave a ton of space here. I do have a little bit at the bottom of the page here, but having done this problem a few times before, if you test for symmetry here, it's not going to work for the y-axis. It's not going to work for the origin, but let's just, by chance, let's just check for the x-axis. So I plug in, for the x-axis, I plug in the opposite of y in for y and x in for x. And look at that, I get, because the opposite of y times the opposite of y is y squared, I get right back to the original problem. So I have symmetry with respect to the x-axis. Now, all that is useful, especially the fact I have some symmetry, because if I graph above the x-axis, I can just reflect the graph below because of the symmetry. But I'm going to plug in some points here. I'm going to plug negative 3 in. Notice I'm plugging in for the y because the x was already all by itself. And I get 9 minus 4, which is 5. If I plug negative 2 in, I get 4 minus 4, which is 0. If I plug negative 1 in, I get negative 1 squared is 1 minus 4 is negative 3. If I plug 0 in, I get x equals negative 4. If I plug 1 in, I get that negative 3. If I plug 2 in, I get 0 again. And if I plug 3 in, I get 5. So I plot the points. Negative 5, 1, 2, 3, no, excuse me, I'm sorry, positive 5, negative 3. Positive 5, 1, 2, 3, 4, 5, negative 3, 1, 2, 3, down here. Okay, let's see if that's lined up there. Let's make that a little bit lower. There we go. And then I'm going to plot 0, negative 2. That's right here. And then I'm going to plug negative 3, negative 1. 1, 2, 3, negative 1. And then I'm going to have negative 4, 0. That's right here. And then I'm going to have negative 3, 1. I'm going to have 0, 2. and I'm going to have 5, 3. And it is a parabola. It's just not a quadratic function, but it is a parabola. It just opens to the right. I can do this halfway neatly here, and halfway neatly would have been nice. It's not too good, but I think it's good enough. When you're using your graph paper, it's going to be a lot easier to keep your graphs neat and as precise as possible. All right. Now, that's with one equation in two variables. If you have two equations with two variables, then you're going to get two graphs, and the graphs may intersect, and we may be interested in finding that because there are many applications where you're solving a system, and the first one that comes to mind, that I can think of anyway, has to do with like a break-even point for a business. When you look at the cost and the revenue functions, the break-even point are where the point that they have in common. So we want to be able to find a point of intersection given two graphs, because that's the point that, of course, that satisfies both equations. And we know different methods from our Algebra 1 and Algebra 2 days: the substitution method, linear combination method, or sometimes it's called the addition method, and also the graphing method. Now, the graphing method means graph the two lines and look to see where they cross. That's not always the most exact way, because it's only as good as you can graph them. If your graph is off a little bit, then your points of intersection are going to be off a little bit. All right, so now we want to find the point or points of intersection of the graphs of these two equations. Now, if you remember from your algebra days, this is the equation of a line, and this turns out to be the equation of a parabola. So they might intersect at 0 points. They might be intersecting at a single point where the line is tangent to the graph of the parabola, or they might intersect in 2 points. Now, to do that, and because of the way this is set up, I'm going to probably use method 1. I already have one equation where I have one of the variables isolated on one side. So I am going to take that, and I'm going to use that expression x minus 1 in for y and substitute it into the y value on the other equation. Oh, there goes my music, doggone it. So I have x minus 1 minus x squared is equal to negative 3. So that's going to give me the opposite of x squared plus x minus 1 is equal to negative 3. I'm going to add 3 to both sides. The opposite of x squared plus x plus 2 if I add 3 to both sides. And then I'm going to multiply through by negative 1, and I get x squared minus x minus 2 is equal to 0. Because this is a quadratic equation, and I want to factor it, and I prefer factoring with a lead coefficient that is positive. And as it turns out, this factors nicely. I get x is equal to 2, or x is equal to negative 1. Remember, if this factor times this factor is 0, then by the zero product property, either this factor is 0 or this factor is 0 or both, and that's what I do. I set this equal to 0 and this equal to 0, and I solve. So I'm going to have 2 points of intersection. I'm going to have the point 2 something and the point negative 1 something. Now, to find the somethings, I'm going to plug back in, and you can use either equation, but I'm going to take the simplest looking one that already has the y isolated. I'll plug 2 in. 2 minus 1 is 1. And I'll plug negative 1 in. Negative 1 minus 1 is negative 2. And I have those 2 points. Now, what would be a good check? Well, what would be a good check would be to go and graph these on, let's say, your graphing calculator here. So I'll graph x minus 1. And I'll graph, I would have to add x squared to both sides. I'm going to graph x squared minus 3. And it would look like this. And then I hit graph. There's the line. There's my parabola. And as you can see, my points of intersection, let's see if I can do this by looking at the screen, run right there. That would be the negative 1, negative 2 point, and then this one right up here, which appears to be the 2, 1 point. You could, of course, use trace and find it that way as well. Now, speaking of applications, as he picks up the pace here, as I've already made this video too long, there are real-life applications of mathematics that are going to use equations. We use it to model the behavior or whatever it is that we're describing. As I mentioned before, it might be something to do with money, with revenue and cost. It could be a lot of different things. So we get a bunch of data, and we plot those points, and we want to find an equation that models it. Well, your graphing calculator will allow you to do that Fortunately, other than like linear models, which we're going to discuss in the next section, you really don't need to be able to do that so much for the AP exam. However, it is not that difficult. It's just a matter of entering in all the data and then the right sequence of buttons to find the proper curve of, sometimes best curve of best fit, line of best fit, whatever it is that our data describes. So that's it for the very first video. I feel like I did so much work on this that I should at least get a little bit, if you can still hear me, that I should get a little bit of applause. So since there's nobody here, I'll just give myself a little bit of applause. All right, and you should be ready to tackle some of the problems from section 1 of the prerequisite chapter.